This is our day one video for Unit 8. So in this unit we'll be focusing on sequences and series. So today we're just going to go over basics with sequences, notation, definition, what a sequence is, and how we can find terms in a sequence. So first thing we'll start with is the definition. So a sequence and this is our notation we have. AN is a function whose domain is a set of positive integers. Which we can abbreviate, say Z plus is another way of, a shorthand way of saying set of positive integers. The function values and these are what we call the terms of the sequence. So the y values are what we call terms of the sequence. Are represented this way. A1, A2, A3, AN, and keeps going. So this is our definition. So what we're going to do real quick is just kind of break this down a little bit. So this notation we have here, this AN, this is what we call our sequence notation. This notation we use to represent a sequence is at A sub n. At the bottom, all the A1s, A2, these are the terms of the sequence. Right, so what A1 represents is that's the first term. Right, A2 would be second term, A3, so on. And one thing you have to be comfortable with is this the nth term notation. This is called the nth term, or the general term. That describes how we get, how we formulate the numbers that make up the sequence. So we can have sequences that stop, so a sequence of n terms, right, so n is a positive integer. It's called a finite sequence. So a sequence that has a last term, has an nth term. A sequence that doesn't stop at n terms, just keeps going, is called an infinite sequence. So a finite and infinite sequence. Before we move on to the next page, talk about generating terms of sequence. There's one piece of notation you also want to go over, which is this z plus we used to represent positive integers. This is a shorthand notation. There's some shorthand notations you might see used in your other math courses to represent different kinds of numbers. So sometimes the real number is represented by r. Integers be represented by z. And that's why positive integers we represent with z plus. You might also see rational numbers are represented with a q. And complex numbers sometimes are represented with a c or sometimes an f. So this is just some notation you might see used in some later math classes. It's just shorthand ways of writing these different sets that we refer to a lot, like real numbers. Instead of using our interval, negative to infinity, we can just write an r. Or integers, instead of writing out -2, -1, 0, 1, 2, and dot, dot, dot on either side, we can just write z. So what we're going to do next is talk about how we actually generate terms in a sequence. So here's two examples of what a sequence would look like. Again, AN describes our general term. And tells us the rule here for how we generate terms for the sequence. So we start our sequences at 1 with the first term. So for A1, we're plugging in n equals 1. So A1 would be, on this one on the left, 3 times 1 plus 4. That's 3 plus 4, 7. Same idea for A2. We're plugging in n equals 2, which means the second term of the sequence. So A2 would be 3 times 2 plus 4, which would be 10. Right, same idea, A3, we plug in n equals 3 and evaluate. So that's 3 times 3 plus 4, 13. And the last one, A4, plugging in n equals 4, and the same idea. 3 times 4 plus 4 makes 16. So those are the first 4 terms of the sequence. It will be 7, 10, 13, 16. And we keep going from there. One on the right is the same idea. We want to generate the first 4 terms of the sequence. We're just going to plug in n equals 1, then 2, then 3, then 4. So for finding the first term, A1, we're going to plug in 1 for n. So -1 to the first over 3 to the first minus 1. So that would be -1 over 3 minus 1, -1/2. Alright, find A2, same thing. -1 squared over 3 squared minus 1. That'd be a +1 over 9 minus 1, make positive 1 over 8. A to the third, we're plugging in n equals 3, so -1 to the third, 3 to the third minus 1. So that would be negative 1, 27 minus 1, make a negative 1 over 26. And last one, plugging in a 4, negative 1 to the fourth, or 3 to the fourth minus 1. So that'd be a positive 1 over 81 minus 1, to make a positive 1 over 80. So there's our first four terms. We can write those out in our sequence: negative 1 half, 1 over 8, negative 1 over 26, and 1 over 80. You can see that by using the negative 1 raising to the n power, all my odd terms will be negative, and all the even terms will be positive. So you get an alternating sequence there. So one thing we'll be doing with our sequences is adding up these sequences, adding up the first n terms, and then build up to adding up the sequence infinitely. So we're going to start with the notation that we use for that, called summation notation. So this notation here is for the sum of the first n terms of a sequence. And this is our notation we have for it down here. This is called our summation notation. So this right here is our summation notation. So we're going to kind of pick each piece of this notation apart and kind of talk about what it represents. So this big Greek letter here, this is called a sigma. And this is a Greek letter that always indicates a sum. You'll see this used again in other math courses. It always indicates a sum. And sometimes, since it indicates a sum, sometimes summation notation is also referred to as sigma notation. So this I you see down here, this is called the index of summation. And you see numbers on bottom and the top tell you which numbers you're actually adding together. So the one on the bottom is called the lower limit of summation. And the one on the top is called the upper limit of summation. So the reason we use this notation instead of writing it out is because this is the same thing as if we were to actually write out A1 plus A2 plus A3 plus, and just keep going until we got all the way up to AN. Right, so they mean the same thing, but this is a much more compact way of writing it. So that's why I want to use this notation, because it makes it easier to write things instead of having to write all the way across our entire page. We can use this nice, concise notation. Alright, so we're going to do a couple examples of expanding and evaluating a sum. So first example, be the sum from 1 to to 6 of I squared plus 1. Right, so what this means is we have to actually generate terms 1 through 6 of the sequence and then add them together. So I start by finding the first term in the sequence, which would be 1 squared plus 1, which would be 2. Right, and find the second term, which would be 2 squared plus 1, which would be 5. Right, and I keep going. I equals 3. 3 squared plus 1, that's 10. I equals 4, be 4 squared plus 1, 17. 5, be 5 squared plus 1, 26. And finally we get to 6, will be 6 squared plus 1, 36, 37. Now what the summation notation is telling us to do is add all these terms together. So we're going to add 2, 5, 10, 17, 26, 37. So 2 and 5 is 7, and 10 is 17, 17 is 34, and 26 would make 60, and 37 would make 97. So one thing to make sure when you're evaluating these sequences, make sure that when you're doing the sum, that the index for summation matches what's actually under the sum. Anything that doesn't match that index, you can't sum that. You can't plug in. So I'll do an example down here. If there's no index in our sum, so take the sum from 1 to 5 of 3. Right, there's no I there, it's not 3I, so all I'm doing here is just adding 3 5 times. Alright, so our index is I, there's no I's in the sum. And last thing we're going to do is we're going to work the other way. We're going to take a sum that's expanded and we're going to rewrite it using our summation notation. So, first example, I had a sum 1 to the third plus 2 to the third plus 3 to the third, 4 to the third, keep going, all the way up to 7 to the third. I'm going to write that using our summation notation. So first thing we do is we need our sigma, our sum symbol. We need an index. Right, and next thing we need to do is look at what our first and last term are. Right, so here's my first term is 1. So this will be my lower limit. Then it runs all the way up to 7 to the third. So 7th term will be my upper limit. And next thing we need to look at what the rule is. The general term is we take n for this sequence and raise it to the third power. Whatever term number it is, we cube it, raise it to the third power. So writing this in sum notation, that means my index is I, so the sum of I to the third from 1 to 7. So that's how we would write that using our sum notation. You see it's a lot more compact than having to write out all 7 terms. sometimes the sequence you'll be writing in some notation will be written out um, in general form. It won't actually stop. It'll go up to the nth term. That's what we're going to do here, an example of that. So if I have 1 plus 1/3 plus 1/9 plus 1/27 plus, in our general term, 1/3 to the n minus 1. So again, this is our first term, our lower limit. This is our final term here. Is the nth term is our upper limit. So I'm going to put this in our sum notation. We start with our sigma. I equals 1, and our upper limit this time is n. And then they give us the rule right here already by saying what the general term of the sequence is. We're going to use our index, so 3 to the I minus 1. So that's it for this video. If you're looking for any other resources, better explanation for any of this stuff, you can search for sequence notation for the first part of the video and summation notation for the second part of the video.